Hello everyone, welcome to this first talk in our new 3D GV seminar series on 3D computer vision and 3D geometry. So the idea behind this is that we want to continue the academic dialogue despite the travel restrictions that we currently have due to the COVID crisis. And we do this through a virtual seminar series on 3D vision geometry processing, where the idea is that we will have talks by experts in the field on a weekly basis. And this was inspired by similar series in other fields, such as robotics today. We will stream the talks on YouTube, so it's easy to attend for free, and you can ask questions using the chat, and we will then relay questions to the speaker. In practice, we will have the talks on Wednesday, with some exceptions, and we have speakers from Asia, Europe, and North America. So we will actually rotate through the different time zones based on where the speaker is located. You can see this on the left. So we'll start today with Marc Pollefeys, and next week we'll have Katarina Fragiadaki from Carnegie Mellon, and then Xing Tong from Microsoft Research Asia. We will make the recordings. The recordings will stay online. But you should regularly check the workshop, the seminar website for the schedule and the streaming links. If you're confused by time zones, such as me, there is a calendar on the workshop website where you can simply add the dates to your Google Calendar, and they will automatically be converted to the right time zone.
Hey, Torsten, quick interruption. Yep. We're still sharing Mark's screen, not your screen.
Oh,
I believe.
Wait.
So if you want people to see these links and things, they're probably not seeing them.
Wait, let me try this again. Can you see my screen now?
Mm-hmm.
Okay, perfect. Okay, so sorry for the confusion. Let me start again. So welcome to the this first talk in the 3D GV seminar series on 3D vision and geometry. The idea is that we want to continue the academic dialogue despite travel restrictions due to COVID. So we will introduce this new virtual seminar series on 3D vision geometry processing, which will essentially be a series of talks by experts. It's inspired by similar series in other fields, such as robotics today. And it will be easy to attend the talks and ask questions using the YouTube's live stream that we put.
Apparently the YouTube folks did see. Apparently YouTube folks did see your talk, so you can.
Angela from Munich, Angela Yao from NUS, Angju Kanazawa, Yuyong Zhang, Zixing Wang, myself, and Yasutaka Furukawa. We are very happy to get the support from a set of senior supervisors in Bao Kuang Chen, Jana Kosechka, Yetira Malik, Leo Guibas, Lourdes Agapito, Michael Black, and Richard Hartley. And Michael is actually also here in the Zoom room and will introduce Mark, our first speaker. But as a quick reminder, please regularly check the workshop website or seminar website for details and updates. And with that, I will hand it over to Michael.
All right, thanks. I'm Michael Black, and it's my honor to introduce Marc Pollefeys. We couldn't have a better first speaker for this series on 3D geometric vision. Marc, for people who don't know, is from Belgium. He did his undergraduate, master's, and graduate work at KU Leuven. Graduated with his PhD in applied science in 1999, did some postdoctoral work, and then moved to the University of North Carolina at Chapel Hill as an assistant professor. There he won a number of awards, including the Packard Fellowship for Science and Technology, the NSF Career Award. Oh, and I forgot to mention that he also won the Marr Prize for Best Paper at ICCV in 1998. He then moved back to Europe, to the ETH Zurich in 2007, where he's a full professor of computer science. In addition to that, he's also the director of mixed reality and AI in the Microsoft Zurich Research Lab. and the director of science, leading a team of scientists and engineers who are developing advanced perception capabilities for the HoloLens. So he leads a dual life like many of us these days. Marc is an expert in 3D geometry. Some of his early work involved estimating structure from motion, particularly interesting work on dealing with articulated objects. He's interested in humans, objects, scenes, buildings, cities, reconstructing all of that, and not just reconstructing the geometric information, but exploiting how the semantics of objects and scenes relate to geometry. So without any further ado, it's a great pleasure to welcome Marc Pollefeys.
Thank you. I hope you can hear me. So first, I wanted to thank the organizers for inviting me. Obviously gladly accepted. I think this is a fantastic initiative. I might have made a mistake of accepting this right after ECCV, where I had a whole number of other things to prepare for and so on. So we'll see how it goes. But essentially what I want to talk about today is first a little bit, give you a little bit of an overview of these kind of image to 3D pipelines and how we've kind of been working on this over the years with, I think, quite some amazing progress. But then dive in a few recent results. You'll see a selection of some recent ECCV and CVPR papers in particular on those topics. Things as basic as feature matching, still things to be done there, also using classical methods. Then some calibration-free structural motion as well as calibration methods. And then also, I always, as Michael was saying, I'm interested in reconstruction, but also really the combination with semantic. So we'll look a little bit at that, not too much in detail though, given limited time. And then also I want to end with talking about image-based localization, which is one of the main topics I focus on also at Microsoft. And in particular, also there's some done on the research side, some privacy preserving work in that space. Okay, so as Michael mentioned, long ago we started really, and I think we're the first ones to actually assemble a full 3D reconstruction pipeline, starting from images step by step, relating pairwise how images are relatively positioned with respect to each other, then assemble all of that using structural motion techniques to self-calibration, then revisit the images at like in a dense, every pixel being revisited, doing stereo matching, multi-view, then stereo matching, and then eventually assembling all of this into a 3D model. So this was essentially the first pipeline that brought all of this together. Here's kind of one of the nice examples back then. This was recorded from a video sequence. We could track using KLT features along the way, and then from that build up essentially everything up to a dense detailed 3D model from a handheld video camera. And we were able to demonstrate a precision of about 1 in 500, which given an input image of 500 by 700 was actually really good. So that's what you could do at a time. However, there were big challenges. Either you had to get a dense video sequence, or you really had to be a PhD in computer vision to know how to take photographs to be able to have the algorithms work. That all changed once David Lowe proposed SIFT features. So we really had big progress in feature matching, enabling us to just start assembling essentially photo collections. So this is work by others, great work. In particular, the work by Noah Snavely was quite impressive, in particular on the application side of what you could do from photo collections, and really kind of stimulated that whole area of research with lots of work over the years. In that, one of the things the points I'd like to highlight is my PhD student, Chang Wu from UNC, did some amazing work in actually making this accessible to the community by building visual SFM. Of course, also Yasu here, who's here, also did some quite amazing work with PMVS that could be coupled to this also. But essentially the structural motion part, Chang received the Mark Everingham Prize 2 years ago for this at ECCV, for essentially making these kind of structural motion algorithms, which which beyond kind of the progress we had made on understanding the problem, still needed some strong engineering to really deliver good solid methods that could be applied to photo collections. Then building further on that at UNC, seeing the interest in assembling things from photo collection and people trying to scale this up. And having, as Michael mentioned, done a lot of work on doing really fast reconstructions in cities with streams of video data being processed in real time thanks to GPUs and so on, we decided to also show how we could scale this up. And so here you see some of the work in that space. This was work with Jan-Michael Fram at UNC, where we process essentially in the order of 3 million images on one PC in 24 hours, showing that we didn't need at the time a cloud computing resources to be able to tackle these size of problems. And by essentially building a very efficient pipeline, we ended up registering about 10% of those images from Rome, ended up with 60,000 3D models. This actually included also not only the sparse modeling, but also, as you can see here, dense modeling using some very fast methods we had developed. Okay. So a lot of this research continued. Another PhD student, Johannes Schönberger, did some amazing work on engineering a new pipeline called ColMap. This one actually, very proud that Johannes is the second PhD to get the Marc Everingham Prize at this year's ECCV for ColMap, which is now essentially one of the default tools that people use for both structural motion and multi-view stereo if they need a pipeline, and so enables other people to build on top of this. Okay, so is everything solved? Not quite in those areas. So in particular, I'll show you some very recent results here from our group, looking at a number of different topics. So in particular, if we look at image matching, there's been a lot of effort on trying to go towards more and more invariant, methods that can provide more and more invariance in feature matching. But it's always been clear that this invariance comes at a cost, where you lose discrimination as you build in more invariance. So what we're looking for is to actually do the right trade-off and do this adaptively from the data. So here's a very simple example where you have SIFT on the one hand here, which works great, including when there are rotations, but is less discriminative. And so when you have a scene where things are more ambiguous, it can be harder to find good matches. But if you use something like upright SIFT, which doesn't look for the orientation, but actually uses the kind of given vertical orientation, you can actually, on the same images with the same descriptors, except that one is always computed vertically, while the other one is actually aligned to the dominant image gradient, you can actually still much better discriminate and therefore get much better results. Okay? So what we've built is a method, we call it Lizard, a method that will essentially look at the image data, and depending on the content, will pick the right level of invariance that's needed to do the matching. So how does it work? We start from an image. We have a CNN backbone. We extract semi-dense features, feature maps, and then we have different heads that compute different types of invariant features. Features that are invariant to different variant or invariant to different types of properties. In particular, in this example, we had rotation invariance and illumination invariance. And we could do all combinations where, of course, the more invariant you are, the less discriminative you are. And so we compute all of those. We also compute this kind of more global context using some NetVLAD essentially. And we'll see how we can then combine those two, both the local descriptors as well as the global descriptors into a very effective matching scheme. So in particular, what we do is we have a distance, which is here, the final distance that we use is a weighted linear combination of all the different invariant descriptors that we've computed, the more invariant and the less invariant ones, the more specialized one and less specialized ones. And the way we weight this is adaptive to the image content and the image context. Okay, so if in the middle region here we see that things are upright, but there's some lighting changes, then we will in particular select or prefer to use the distance that actually builds in the right level of invariance. Okay. Here's this in action. So you see initially with the very simple, just two choices, upright shift or shift. Initially, it's picking upright shift everywhere until there's rotation showing up, when upright shift will break down. And essentially, our lizard mechanism will automatically detect this and then switch to using shift, as it's then, for that part of the image, the more appropriate method to use. Here showing this in action, this is actually the day-night image data set, but augmented with rotation. So we both have lighting changes as well as rotation changes. And then our method can correctly, if you have a day reference and you try to match it to the night, there's a big difference. And essentially our method can nicely cope with this while all the existing state-of-the-art methods are struggling. If you start from a night reference, the problem is slightly easier. We see that our method still performs the best, but some of the other methods are now getting much closer. Okay, so also code is available here if you're interested. Another work that was also presented at ECCV from my group, from Luca Cavalli and postdocs and myself, is work where we essentially show that handcrafted methods are still very competitive. And of course, there we understand exactly the steps we do. So here, for example, we compute simply nearest neighbors. You see some inliers and a lot of outliers. Then we look at region correspondences, so get consensus by doing a fine kind of region correspondences. What is important, what we do is determine per region thresholds on how consistent matches need to be within the region. Obviously, this affine matches really only model a planar region without strong perspective effect. And so depending on how planar the region is and how much perspective there is, based also on the size of the region and so on, we would need different thresholds. And so it's really important to have this method to determine adaptively what the threshold is. And then essentially we can filter away inconsistent matches and end up with essentially a very reliable set of matches with very few outliers still included. If we compare this to state-of-the-art methods, this method actually outperforms essentially all of the existing methods, both the handcrafted ones as well as the deep learned ones. Here you see some other examples here just with upright shift. And you can see that essentially this method works better than other ones on the Aachen day-night. Here it's interesting. So we have much better descriptors here that are much more invariant and better suited to the Aachen day-night. But we see that something as simple as upright root shift plus our method actually can catch up and make up most of the gap, with respect to these better descriptors. And also, this is actually something that's really, really fast and very efficient to run in parallel. And you're obviously invited to download the code and try it out yourself. Then yet another method on essentially improving different pieces of the pipeline. So typically when we match, so differently than when we track. So when we track, what we do is we start from one patch in one image, and then we try to really determine the best motion vector to the, find the best patch in the next image that corresponds to this. And so really refine it based on looking at both patches at the same time. Typically, when we do structural motion from photo collections with invariant feature matching, we actually extract the features independently in the different images. And essentially, people don't refine this afterwards. So what this paper is doing essentially is something very simple in hindsight, is simply looking at the two patches and given the two patches, determine the best, an updated, improved correspondence that better corresponds to matching, precisely a point in one image to the best matching point in the other image. Okay. So it works as follows. So we extract the features. We do this feature matching. So this is the standard pipeline: feature extraction, feature matching, and then structural motion. What we propose to do here is simply insert a few steps. In particular, here, this refinement step, which, given the two patches, which could be under quite some wide changes, we will use now a network that looks at both patches, an input, a source patch and a target patch, and we use a network in both directions. But it will essentially, given the source patch and the target patch, it will predict the best warp from this patch to that patch, and therefore also predict the best correspondence, and vice versa. And so we build up then a graph of all these corrected correspondences. And then when we have more than two correspondences, when we have a set of tracks that become longer, we actually do a multi-view optimization on those to get consistency across the multiple views. This is what is then being done here. And then these refined multi-view correspondences are now fed into the structural motion. Okay. So what we see is when we do this, we essentially get systematically improvements in all the numbers and with all types of features. If we have SIFT, or we have refined SIFT, or D2 features and refined D2 features, etc., if you look everywhere, we get significant improvements on our results in the reconstruction. Here's some other results. Also here, strong improvements. You see that actually in this case, SIFT essentially has no improvement, but all of the other types of features strongly benefit from this. This is because in this case, SIFT is already, in a sense, saturating for camera relocalization. Here's some other examples. See here, actually, SIFT is not saturated. You do get an improvement. There is essentially a systematic improvement by this method, independently of what feature detector we start from. And here again, in a local feature evaluation benchmark, significant improvements. Here's also a visual representation of this. So you see this toggling between red and green. The red is the classical method, the green is the refined method. And if you look carefully, for example, at the roof or at the regularity of the reconstruction, you can see that the green reconstruction looks a lot more crisp. Look, for example, at the roof line, you will see it is much straighter, much less noise on the reconstruction. And so all of this is actually quite simple step to insert after the feature matching stage and before the structural motion. You can simply insert this and then you get this benefit. And so here also the code is available. Okay, so now let's switch gears to structural motion itself. And so in this work, which again was also just shown at ECCV, we have a calibration-free structural motion method. So in particular here we use, we can use cameras, including highly distorted cameras with strong radial distortion like fisheye cameras or cathodic optic cameras, without needing to know the calibration in advance. We can build up, or even ever knowing it, we can build up the whole 3D reconstruction. So what's the principle? Starting from these type of images, here you see Victor, who was the main driver of this work. Like the advantage of the method, and instead of just actually a posteriori trying to cope with the strong distortion in a bundle adjustment and refine the radial distortion, and CalMap would, out of the box deliver something like this, not being able to recuperate the strong distortion, this method can actually cope nicely with it. The whole idea is actually to first focus on a camera, on looking at a camera as a 1D measurement device instead of a 2D measurement device. Okay, so if you look at this, independently of the radial distortion, what you can notice is that this feature point here, independently of the distortion, it just moves along this line. But the position, if we decompose this in which line and then the distance along the line, the first part of this, which radial line we have, that's actually something that's invariant to an arbitrary distortion. Okay, so in principle, what we use is a 1D radial camera. This is a model that I've been using in a number of different works. And here also, we use this camera to decouple the need for calibration from the actual structural motion. Okay, so we're really initially looking at our cameras as just this 1D measurement device, and it just tells us in what orientation, what plane in the world our 3D point is located on. So we get one measurement instead of two. Classical camera looks like this with rotations and calibration, so intrinsics and extrinsics. Simplify it like this with a square pixel and a center principal point. The radial camera then looks like this. Essentially, those two numbers here. So we drop the last row, and then we essentially get a radial camera. And so the radial camera ends up just looking like this, with this being, this being a tree vector that represents the first and the second row of the rotation matrix and the first two components of the translation vector. Under the assumption of square pixel and center principal point, we also have these constraints that have to be valid. So although it's uncalibrated in terms of radial distortion and focal length, we are actually assuming that it's a calibrated, square pixels and central principal point. Okay, so the method works as follows. With these different steps. The first step is actually to be able to initialize this reconstruction. And this is actually the hardest part. So first, because we only have a single constraint per observed point from a single camera, we need, and so each of those observed points gives us now one back projected plane as a constraint. If we arbitrarily back project three planes, we will always have an intersection. So we actually don't have a constraint. So we need to at least have 4 views of the same point to have an overdetermined system from which we can start to get calibration constraints. Okay? So 2-view reconstruction is in this case not possible. The natural method would be to use the radial quadrifocal tensor, which I introduced with Tirtala actually in 2005, but then we had the IGCV paper in 2012. But the problem is that this quadrifocal tensor is just too complicated to compute, and also finding in 4 views enough constraints is actually quite hard. And so in practice, so here we propose a different method. In particular, we'll initialize first from 3 views. We'll initialize a 3-view setup, and then we'll add 2 additional views to complement the reconstruction. Okay, so it goes as follows. We start with the radial trifocal tensor. We need here a slightly non-generic positioning of the cameras, but it's actually one that happens all the time in practice. This is the natural way that you will actually capture pictures in most settings. So in particular, the constraint we need is that those radial cameras, which essentially are defined by one optical axis, the optical axis around which all these planes rotate, these constraint planes for points, that these optical axes, we need 3 cameras. In all our set of cameras, we need 3 cameras that have intersecting optical axes. Okay, so the trivial case is, of course, the pure rotation. In this case, we have 3 optical axes intersecting in the rotation point. But there's actually additional cases that are also very typical in practice. One is the typical panoramic motion. This is not when you rotate purely around the center of projection, but when you're actually holding the camera out and essentially rotating around. This is in practice what people do when they take panoramic images. In that case, as you can see here on the right, you actually still have typically an approximately intersecting optical axis. Even more interesting is when you're actually trying to reconstruct an object, and so you keep the object roughly fixed at the center of the view. So you fixate the object and you rotate around the object. This is orbital motion. Also in this case, the optical axis will approximately intersect. Actually, this is something we realized was a degenerate case for some self-calibration work we did 20 years ago, and created a lot of problems for us because it turned out that people often tend to do these type of motions. However, in this case, this is actually what enables us to do this work. Okay, we get essentially these trifocal tensor. We get an additional constraint from the calibration, from the fact that we have these rotation matrix constraints in this, and the fact that they intersect means we can put a translation to 0 in this 2-vector translation. Okay, and you can compare this to the essential matrix, which has also calibration constraints. It's a very similar constraint here. Okay, so first step, initializing this. So we essentially have, a number of correspondences. We fixate an object, we have a number of correspondences, and we compute essentially this synthetic 2-view camera. So by computing the trifocal tensor, we can reconstruct a 2D view from this central point, the point where the optical axis intersect. Okay, so these 3 views now get converted through the trifocal tensor. These 3 one-dimensional views get converted to 1 2-dimensional view from the center of these 3 cameras here, where these 3 optical axes intersect. So that's the first step. And then in a second step, we have now this synthetic 2D camera, and we add 2 more 1D cameras to it, or radial cameras to it. And so this set of now the 2D plus the 2 1D cameras, this allows us to compute a mixed trifocal tensor. Okay, and so this is 2 constraints. This gives 2 constraints. This each gives 1 constraint. This gives us the 4 constraints, that have redundancy to enable calibration. So it essentially looks like as follows. Here's an example of the minimal set to initialize. We have 3 intersecting optical axes here, and then 2 additional ones that enable to compute this minimal initialization from 5 images in this case. Okay, then we can do resectioning, triangulation. So once we have this, we can actually compute these optical axes in 3D, then do the triangulation. By essentially, we need now a minimum of 3 views to do a point triangulation. Now we don't need redundancy. We just need 3 planes to intersect. That defines a point. So if we have points that are seen in at least 3 views, we can triangulate them. And then we can finish eventually with a bundle adjustment that will then refine all of the poses and impose all of these one-dimensional constraints in all of the images, all jointly estimating the 3D structure as well as all the 1D camera poses. Okay. Here's some of the 3D results that we get from this. So you see that without needing to calibrate the camera, with arbitrary radial distortion, we can get this quality of reconstruction. They're essentially all integrated now in Colmap also, if you're interested in using these type of methods. Okay, and so here you see in particular, some strongly distorted input images, even catadioptric ones here, and the reconstructions we obtain from that. Okay, so we can continue with using these 1D cameras. So I actually really like these 1D cameras. And so here we'll actually have a new multi-camera calibration method that also leverages the flexibility of this radial camera model. So in particular, it's infrastructure-based calibration. So we assume that we somehow have, from other sensors or some other way, obtained a 3D model of the environment. And then we have, with our multi-camera set, we capture a number of images of this 3D reconstructed environment. Okay? And so using those 2, we now want to obtain a calibration. So we don't use a calibration pattern by itself. We actually use the scene as a calibration pattern. Okay. So what we do is, for each of those frame sets, let's say we have 1, 2, 3 different frame sets here. Not all the cameras necessarily will have enough correspondences to determine their unambiguous pose. But let's say that always a subset of these cameras can be determined. We determine these poses. From this, we compute a partial calibration, which is essentially of the extrinsic. This is essentially the part that corresponds to the radial camera. And then in a second stage, we can then refine this and compute both the intrinsics and the extrinsic, the full intrinsics and extrinsics for this multi-camera rig, and of course end up with a band adjustment. Okay? So it goes as follows. Each of the sets of frames captured by the rig, of which a subset of the images we would be able to compute a pose for. depending on what we are seeing in what views. So we get a relative pose between some of the cameras, which can vary over the different multi-view frames that we capture. Taking all of this together, we can average this and get essentially an initialization for our camera rig calibration. The partial one, we can do a multi-view optimization of this and a radial bundle adjustment and get an improved partial calibration of our setting, and then switch to a second stage where now we can upgrade these radial cameras to full cameras, starting from this rig here, and then end, of course, with the final bundle adjustment. So here's an example of an autonomous robot, gardening robot. So in the full configuration, it actually has an arm with a tool on that can cut hedges and so on. But essentially, we have a camera ring here. And that camera ring needs to be calibrated. It has essentially these 5 stereo pairs. And of course, one stereo pair doesn't overlap with the other stereo pair or barely overlaps. So it's hard to calibrate it all at once with just calibration boards. But our method here can essentially, by just looking at the garden that was reconstructed before, can calibrate itself and get actually quite close to ground truth calibration. Okay, but if you want actually even more accuracy in your camera calibration, then we have this method for you. So this was work presented at CVPR. The main author here is Thomas Schöps, who recently graduated from my group. So why is 10,000 parameters better than just a dozen? Okay, so what we do is we actually get this this calibration pattern that Thomas spent a lot of effort on designing a calibration pattern that would give it the most accuracy, in particular using the symmetry of this pattern to really get highly accurate center points here. We get many images of this so that we can really over-constrain our calibration. Okay, so we initialize this. We use actually a model that's very flexible that will essentially put a grid over the image and then determine for each point how it gets mapped, and then determine for any point based on the neighboring points, actually like this, using a B-spline interpolation, will actually determine the calibration for this point given the calibration for the nearby reference points. And we can actually both do this as a normal 2D image warp calibration, or we can even do a non-central model if we want, in which case we have 2 of those grids to determine arbitrary rays instead of just directions. So why do we do this? Well, here what you look at is a visualization of the residuals after of essentially all of the calibration boards will have in the end some small residuals when you have finalized your bundle adjustment and adjusted everything. Points will not perfectly project. And of course, there's local noise, so it will never be perfect. There will always be some error in exactly where the point is. But if you have a good calibration, you expect these residual errors to be essentially random, in particular random in their orientation. Here, if using a classical thin prism model with 12 parameters for the calibration, and we plot out, based on this color coding here on the right, the direction of the residual that we observe in different parts of the image, we see that there's actually a pretty significant and very strong, clear bias in what is going on. So the residuals here are all pointing outwards, while all the residuals here are pointing inwards, etc. And we see this kind of strange pattern here. Okay, so that means that our model or calibration model failed to fully capture this consistent offset in this consistent bias in the calibration. Okay, here's another model. This is based on the OpenCV 12 parameter camera model, and also here you see a quite consistent, errors in error patterns here. Okay, this is then when we use our method, which has many, many more parameters and can essentially absorb. And so now you see this starts resembling much more a random pattern of just small random variations based on essentially the feature detector not being perfect. This is at 30 pixel cells. yields about 5K parameters, and it's a central generic camera model. If we go to 20 pixels per cell, we get about twice as many parameters, so 10K parameters. If you look, actually, if you squint, you can probably still see some bias here, a slight bias, which is smaller here, and then even smaller here when we go to the fully generic model, which is a non-central generic camera model with 20 pixels per cell and 25K parameters. And you see here that really it's almost impossible to still discern any biased, like any existing bias in this data. Okay, so this essentially yields a much more precise calibration if you spend the effort to do it. Okay, okay, so now let me switch gears to then semantic 3D reconstruction. I'll very briefly go over this, but the key message here is that you should not do 3D reconstruction and semantic classification as two separate problems. It's actually really important to bring all this data that you can extract from the images, this kind of depth measurements, as well as the semantic evidence. And in general, you would want the full, not just per pixel decision, but actually the full distribution. Use all of this information together to get both processes to help each other. Because essentially, if I'm reconstructing a facade, if I know it's a facade, I have geometric priors about it. I expect to find a vertical surface, a mostly smooth vertical surface. If I'm reconstructing a tree, I know that it's an actually quite, like it's a surface that looks very different, that will have a lot of variations, a lot of surface area. I will want to regularize it in a different way. And so my priors about the geometry of the scene very much depends on the semantic interpretation of the scene. And so if I can look at the image and draw conclusions about what type of object I'm looking at, I can actually use that to make a better reconstruction. Vice versa, if I'm reconstructing, a brick surface, but it's a horizontal brick surface, it's likely to be ground rather than a building. If I'm reconstructing a brick vertical facade, then it confirms that it's probably a building. So in both directions, those processes can help each other. Okay, here's actually the process in action. You see on the left a reconstruction that's using purely geometric information. A lot of data missing here. We had poor observations, and so the standard regularization doesn't do a good job at filling in the data. Because filling in a lot of surface area is costly, and the general regularization will just minimize surface area spent on explaining the data. What you see on the right here, which is a top view of the same square, and using exactly the same geometric information, but aided by the semantic observations also, we see that here it will naturally fill in the ground, because ground is expected to be a extended horizontal surface, and so it will naturally kind of extend it out. And then the building here that's not complete, as soon as the ground diffuses under it, it actually knows that it's more likely to stand on the ground, and so it completes itself naturally. Okay, so same geometric information, but qualitatively completely different 3D reconstruction in the end. So in addition to being a semantic reconstruction where that's a richer reconstruction, it's actually also a better geometric reconstruction. Okay. Here's some further examples of this. Also, the fact that here we somehow stuck together the tree and the facade. When we actually have those as two separate classes, it will naturally keep those separate and not somehow fill in, like make random connections somehow, because it saves a little bit of surface area. Okay. Also more useful, you can actually separately, determine the volume of the building, which would not be possible if it was all melted together in one big volume. Okay. I'll very briefly, what you really would like to do is the previous method was translating all the constraints to the 3D volume, and then have both the observations in the volume translated to the volume, as well as the regularization happen in the volume, and they are then optimized and solved for reconstruction. This is actually not what you want to do, ideally. Ideally, you really want to minimize the data discrepancy that you observe in the images, because the observations are image observations, they're not in 3D. And to handle properly visibility and so on, what you actually need to do is take the 3D model, reproject it in the images, and then see if this reprojection actually corresponds to what you had observed in the images. And really, essentially minimize this difference, not do something that's translated in the scene. The regularization, however, still needs to happen in the scene because the priors are on the 3D geometry of the scene. Okay? So that's work we did with Nikolai Savinov. Some really nice work on ray potentials that would essentially have this data term expressed as a high order potential on all of the voxels visible from 1 pixel. This had some non-convexity involved, and it essentially was very expensive because we both had a global 3D view as well as a per camera local volume that would essentially translate the constraint into a volumetric representation of the single view constraint. And then we had, in the optimization, constraints that would enforce the consistency between those two, or one for each view here. And of course, this was quite expensive, but was actually the right thing in terms of problem formulation that fully captures visibility and priors correctly. In the meanwhile, we went back to revisit some of this work, but with deep learning methods, as everyone is doing these days. The key advantage that we found was not necessarily we got much better reconstructions, but we could get them much faster because the properly derived mathematical formulations intrinsically ended up being quite conservative in the step sizes and had to do them, regularized step sizes everywhere the same and get guarantees on the convergence. These were all convex problems that we were minimizing in this case. So I ended up needing many, many iterations to get to a solution, while the learned methods, we can achieve qualitatively the same results with many less iterations when we train on that. Also training a multi-grid representation that allowed us to get there. Some other work here in 3D surface reconstruction. Here, essentially replacing the classical TSDF methods with a learned method. So TSDF is making relatively coarse assumptions about the scene geometry, which are not valid in practice, especially at corners, or if you look at the surface in a slanted orientation and so on. It turns out you can capture a lot of the things correctly if you do deep learning on that, but really it's a very small deep learning problem where you can provide essentially exhaustive coverage with data of all the situations, and then we can essentially get a much more effective depth fusion approach. The reason this works is really because we have, deep learning is often hard when you cannot exhaustively cover the space of all possible, of all the data that you could, encounter once you use the approach. When you can use the geometric structure to actually, in the end, only have to do learn a function that's essentially not too high dimensional, then it works particularly well. And so here you see some of that work when it was presented at CVPR this year. Some other work in that space is our convolutional occupancy networks with Sungyu Peng as the main author. This was also work with Andreas Geiger's lab in Tübingen. The key idea is really that the standard methods will essentially, deep learning methods that will predict occupancy will look at the points, encode that, and then represent that. The key was to not do that globally for the volume, where typically these things only work for a specific class of objects that you can learn, but actually do it in a convolutional nature, where you can essentially decode for every point based on the local neighborhood and then predict occupancy based on that. And so you can actually, by having this local estimation everywhere in the volume, you can actually get this type of very nice results in terms of reconstructing a surface from a disorganized point cloud or from any other type of measurements of the scene geometry. The last topic I wanted to talk about briefly is image-based localization. Obviously, this work that I've been doing a lot of work with Torsten on this when he was here in the lab. So key principle is we have a 3D model, a map of the world, we have query images, we extract features, and then from those matches, these 2D, 3D correspondences, we compute our camera pose. Here's one of the methods we developed with Bernhard Seissel, which was a voting scheme, which meant that we could scale very nicely to very large number of features because we could linearly traverse the features, and essentially every feature would vote on a plausible set of locations from which it could have been observed. And by simply voting, we could very quickly and very efficiently accumulate evidence of where the image was taken from. And so this method was very effective and is very nice because it can also have capture multimodal distributions if there's ambiguity or repeated structures in the scene we're looking at. What's interesting to know is that this method is actually at the base of what's now in the Google AR mode in Google Maps. Not surprisingly, Bernhard moved on after his PhD to work with Google and did some amazing work on building on top of this work to deliver this to help deliver this feature. But of course, I'm now working at Microsoft, and one of the big focuses there also is actually this image-based localization. In particular, our version of the AR Cloud service that we are building, and this is called Azure Spatial Anchors. And you see here the type of scenario we want to enable, letting multiple people work together, share a coordinate system. And so one person establishes a local map, and then others can align themselves with respect to that map, all of this facilitated by the cloud. Even more importantly, the goal is that once you establish this local map, next time you come back or someone else comes there, they can actually connect to that coordinate system and therefore also access all of the relevant information, holograms or other information that you have spatially anchored to this representation. Okay. One of the things we did with that was enable Minecraft Earth. And here you see myself actually playing here in Zurich and having relocalized to a particular location. But more importantly, what we're really looking at enabling is more with an always-on HoloLens type device where you're walking through a space, enabling you to be continuously localized with respect to that space. That can both be your enterprise facility, but it can also be the whole wide world. The goal is to essentially cover all of those scenarios. In a kind of cartoon representation, we want to do the following. First person walks around, maps part of the space. That moves from the device to the cloud. Another person walks another part of the space. All of this gets moved to the cloud, and eventually, as you get more coverage, it can all be puzzled back together in an exhaustive map of the whole facility. And then also, as you keep using it, it can essentially stay up to date and refresh itself, etc. Here's an example of about 100 HoloLens sequences, few minutes of walking around in Studio A, which is one of the buildings on the Microsoft campus, and essentially the whole facility being rebuilt from just automatically assembling these small partial maps. And puzzling it all back together, essentially. Now, with this, there are questions about privacy. So it really depends on the scenario. In most scenarios, there are no problems. But in some scenarios, you might really care about not having any data either moved up to the cloud or from the cloud, go back to some clients. If you need to also be able to do localization when you're offline, in an offline scenario, for example. Okay. So one of the problems which was highlighted by Pitaluga et al. This was work by my colleagues at Microsoft Research. So Sudipta Sinha, for example, was one of the main drivers here. The key is that essentially from just the feature points of a 2D or 3D feature map with associated descriptors, it turns out you can step by step really recover something that's very close to the original input image. Okay, so just having 3D points and descriptors is not a guarantee of a privacy-preserving representation. Okay, so here's this in action, Pitaluga's work. You see here the points on the left, and so those have SIF descriptors associated with them. and one color in this case. And from just this one point color plus the SIF descriptor, you can essentially, using their method, generate these type of images where this is the ground truth original video. You see it's scaringly convincing and clearly not preserving much privacy. Let me skip this. Here's some more examples. So the key is, can we somehow develop methods that are privacy preserving? That still allow us to localize, to do what we have built a representation for, but doesn't have the same privacy concerns. Okay? So one approach is client-centric. This is a scenario where I build a map in the cloud, but I want to let a client download the map so that he can locally do the localization. For example, for some offline relocalization scenarios where you're not continuously connected to the cloud. Okay. So how could we do this? Well, essentially, when we look at characterizing a 3D point, as we've seen earlier, it's essentially the intersection of three planes. One way or the other, we have three constraints on the coordinates of the plane, and that essentially nails the three coordinates of the point. Okay. Now, if instead of that, we don't fully determine the point, we leave some ambiguity on the point. So we only use 2 planes instead of 3 planes. Okay, so 2 arbitrary planes that move, that essentially slice through the point. They partially determine the location of the point, but not fully. Okay, they just determine it up to a line. In the first case, if the point is fully determined, we project it in the image, and we'll essentially have a 2D reprojection constraint. So we'll get 2 constraints on the position of the camera given this point of correspondence observation. In the case that we don't fully determine the point, we under-constrain the location of the point, we still can project the line in the image, and we have still 1 constraint, not 2, but just 1, on the camera location, because the point that we observe in the image should still project on should actually align with the projected line in the image. So that's still a one-dimensional constraint. Okay? So the key idea is as follows: starting from a set of 3D points here, we draw random lines through them, and then we forget the actual position of the points, and we just remember the lines. Okay, so we discard the 3 points, just keep the lines, and so we essentially, instead of a point cloud, we have now a line cloud. Okay, so is that helpful to protect privacy? Well, here's an example. So if you look at this, you can try to guess what famous landmark is visible here. Okay, so it's probably not obvious, but as soon as we let the points come through, everybody recognizes the Colosseum. Here's another one. You can try to recognize this. It's probably not obvious. But then once you see the 3D point structure, you can easily recognize it. Here's the last one. And so this is Notre Dame. Okay. Here's some more examples side by side between points and line clouds. And you can see that here we do preserve privacy quite well. There is some limited amount of information that passes through. We are somewhat constrained. Essentially, when 2 points are very close to each other, that implies that the 2 lines going through them, also their minimum distance is bound by the distance between the points. So there is a density still showing where there's a lot of geometry. But this can be mitigated if needed. Okay, so the idea is as follows. Instead of doing P3P, we'll now use P6L, which is essentially having 6 points in the image aligned to 6 lines in space. And it's quite nice because it turned out this problem had been solved. This is actually just a generalized, we can use a generalized relative pose solver for solving this geometry problem. And then if we have more constraints set up with non-vertical or with other things, or if we have multiple views observing, there's all kinds of different methods. What's important to see here is that our methods are the ones in full lines, and the dashed methods are the classical non-privacy preserving methods. Okay, and the same color is essentially the equivalent one. Okay, so you see the P6L is less accurate than the classical one. This is actually also solving a 64-degree polynomial, so it's quite complicated. But if you look at all the other methods that use slightly more constrained setups like non-vertical, etc., you see there the gap becomes much, much smaller. And essentially, you barely lose accuracy while preserving privacy. And it's normal we lose some accuracy because we essentially we can only use half of the constraints than in the classical setting. And you can see that essentially we're in ranges that are quite accurate and completely work well for practical applications in a few centimeters and fractions of degrees are perfectly feasible with this. And many of the methods are actually also quite efficient to estimate. Not the P6L, but many of the other ones are actually quite efficient. Okay. Vice versa, we can also have another situation where the client doesn't trust the server and so doesn't want to send essentially images or data coming out of images that would enable someone on the server side to reconstruct the original image that was sent up using the methods we discussed before. Okay? So in this case, same thing. A point in the image can be seen as the intersection of two lines. And one thing we can do is forget one of those two lines and essentially just keep one instead of two constraints. Now, this is very similar to what we did with the Radial 1D cameras. So in this case, we still have one constraint per point. And so very similarly, we can now, in this case, is just send up that limited information that doesn't enable inversion of the image that's sent up, or the features from the features that I send up, the inversion back to the image, but still will enable us to do relocalization. Okay. So if you look at this here, original image, the features, and then the line, the 2D line cloud. And then we can use that here also to go from a P3P to now back projected planes that have to align to these points. So it's plane 2 points. It's 6 points that have to align to 6 planes. Also here, you see the discrepancy is quite small between the classical method and the privacy preserving method. So perfectly usable methods. And here's some examples here on some benchmarks showing that the end-to-end relocalization essentially works at very comparable rates to the existing classical state-of-the-art. Can we do preserve privacy from both sides? Yes. In some situations, we can actually have both a privacy-preserving map and a privacy-preserving query. And both together can then be aligned in a line-to-line situation. So let me skip this, but showing you essentially here some of the classical method with the features that you send up from this here would actually allow you to reconstruct this from the SIF descriptors and so on. Or method, because all of those features here don't have a corresponding entity in the pre-existing map, we cannot determine where along the line the feature belongs, and therefore we are failing to reconstruct the whole dynamic part or the kind of private part of the image, while the public part, which already exists in the map, that part we can reconstruct. But this one remains privacy preserving. Okay, some more examples. So here's then, to finish, last short video of our latest work that was shown at DCC.
Online structure for motion systems are able to accurately and robustly reconstruct even large-scale scenes from noisy internet datasets. However, previous methods generally assume unrestricted access to all input data and complete control of the reconstruction process. With new commercial applications such as augmented virtual reality and autonomous vehicles, the architecture of the system changes. Instead of running the full pipeline locally, many independent agents collect data and share it with a backend service to process the information. This leads to concerns about data protection, as images can contain a lot of privacy-concerning content that users don't want to share. Although SFM algorithms usually don't require raw images,
and this is Marcel, the first author.
Instead, these features generally contain enough information to reconstruct the input images with high accuracy. For our examples, we use work by Peter Luger and others that was presented at CVPR 19. Spatial and others presented an alternative image feature representation that hides the exact feature position by replacing each key point with a line. They showed that this is sufficient to reliably hide dynamic image content, but still contains enough information to localize the image against the pre-built point map. We build upon their work and present the first full structure for motion pipeline to generate these maps with the same image content protection. Our main contribution consists of a new relative pose estimation method from line features and 4 views with no gravity. Additionally, we combine existing solvers for pose estimation and point triangulation from line features with an adaptive bundle adjustment into a full reconstruction pipeline. We demonstrate the practical applicability of our methods on multiple internet image collection datasets and provide comparisons with the standard SFM pipeline.
So you see privacy concerns, and on the right,
image features for standard SFM,
you see they disappear.
Pretty points in our line-based model.
Okay, so that was it. So in conclusion, there's been a ton of progress on 3D geometric computer vision over the last decades, let's say. We're really at a point where there's a lot of actual usage of this in AR/VR systems, in robotics, and in autonomous driving. What's also important to realize is that naive applications of deep learning end-to-end to many geometric problems doesn't work well or doesn't give good results. Sometimes it will give the impression of giving good results on very limited benchmark datasets, but they often fail in real-world settings. Things like, PostNet, for example, are things that work in very limited settings, but actually don't pan out in the real world and are impossible to deploy. But if you actually leverage the geometric structure of the problem and then learn much more compact, limited parts of the problem, that actually can work really, really nicely. So don't underestimate well-engineered classical methods. They are still essentially competitive in pretty much any area in geometric computer vision. Yes, there's still actually quite some challenges remaining to really move the field forward. Thank you.
Thank you, Marc, for this great talk. We actually have a couple of questions from the audience already in the YouTube chat. I'll read some of them. Whoever wants to ask a question, please type it in the chat box on YouTube and we'll forward it to Marc. The first question was about the local feature invariance learning. And the question is, can deformable convolutions be used for better local invariance selection for descriptors?
I guess they could. I mean, we just started kind of exploring that. I think that there's definitely potential in that, yes.
Another question, or there's multiple questions to the 1D radial camera model. And one question is whether this can be applied to any camera lens or is it specific to a certain family of lens models?
It's pretty much, so the only assumption is really that we know the center of radial distortion, which in practice you can assume to be in the middle of the image with pretty much all the cameras we use. Of course, it doesn't have to be perfect. We can bundle adjust from there to relax that constraint. But that means that for normal perspective camera, you could actually put that point anywhere in the image. But of course, there it doesn't. If it's a perfect perspective camera, the only thing you do is throwing away one of the two constraints that you have for every point. So then you don't necessarily have value in it in using that model. But the strength of the model that is actually valuable, it's actually applicable to any camera, to pretty much any camera, independently of strong radial distortion or not. So yeah, so it's not only for some type of cameras. It's pretty much for any camera. And it essentially fully absorbs or like ignores essentially the radial distortion, but it doesn't have to have radial distortion. It's completely free.
Another question as a follow-up for the 1D SFM paper. It says radial calibration results are impressive, but is there a degenerate case, for example, when 5 cameras, camera views are planar?
Well, for starters, we do need a degenerate situation to have that system work, right? So as I said, we need 3 cameras to intersect in a single, have their optical axis intersect in a single point. I explained this actually happens, even if you don't try to, if you don't pay attention to this will naturally happen in almost any image collection. Now, if you have all of your images, if you take a purely orbital motion, for example, an orbital motion is not degenerate for normal 2D cameras. In our case, if we have an orbital motion, we will have all of our planes go through the center of that orbital motion. And so essentially the only thing we know is like a 2D view of the world as seen from that center of projection. So it's kind of our initialization step. then everything kind of collapses to that, and we cannot retrieve the 3D structure. We can only retrieve the 2D structure of the world as seen from that central viewpoint. So that's probably the most obvious degenerate case for this 1D search for motion. For the rest, I don't think planes or things like that are particularly degenerate more than in general methods. I think what for the calibration planes are can be degenerate. So for estimating the optical axis so in the second part of the calibration part, it would actually be degenerate if you're only looking at a plane, because then the actual optical axis is not determined in the radial case, and so you'd be left with an ambiguity. That's actually why you saw that we couldn't always determine each camera, but only sometimes a subset. So it's the cameras that actually see 3D structure, those can be initialized. The ones that don't only see a plane, you would actually not know where the axis is. It would remain ambiguous.
Thanks. One question about the generic camera calibration, whether the calibration pattern requires some special manufacturing or whether it can simply be printed.
No, it's just printed out, and we actually include in our bundle adjustment, we include the shape of the pattern. So if the pattern is not perfectly planar or anything like this happens, the method will actually absorb that in the final bundle adjustment. That's a lot, that optimizes everything.
There's also a question whether you try to analyze the shift of the principal point among consumer cameras.
Not particularly. So you could obviously, use this highly accurate camera calibration to determine that, but we haven't, calibrated a large set of cameras and analyzed how it behaved and so on. So somebody could actually take our method and verify what happens to all types of cameras. That's not something we have done, but it would be very interesting to do.
Mm-hmm. There was also one question for the privacy preserving part, whether, and this might be more of a clarification issue, whether someone has tried training a neural network that predicts image from line clouds directly.
Not that I know of. We discussed with, so we worked together with Pitaluga and Sinha, who was involved in part, Sudipta Sinha was involved in part of the privacy preserving work also, so both on the attack and on the defense side. And so we discussed the possibility to do that. There were some ideas, but it's definitely a lot harder. So because now you don't know where the feature belongs, it wasn't quite obvious how to do it. It will certainly be a much worse reconstruction. There's a lot more ambiguity left because the feature can slide anywhere along the line instead of being nailed at a position. So it wasn't quite clear how to map it to a network, but we didn't have the time to to explore it in detail, and we didn't really try hard. I would love to see people try it and see what comes out of it, but I don't think it's going to be easy.
I think Yasu also had a question.
Yes, hi Mark. Thank you very much again for the great talk. I asked you a similar question last week at an ECCV workshop, but I want to ask another one. This is about the research versus production. I believe your talk today is more from the eyes of ETH professor, as opposed to Microsoft lab director.
Yes.
From my own experience of academic person, as well as a Google software engineer, some research I was excited, but not excited as an engineer. I would not implement. I wonder, how do you see your sequential research papers? I guess mostly all top-tier conference papers, which you're proud as a researcher. How do you view them as engineering side? Do you actually recommend engineers to implement all those, or are there any work which you're excited as a research papers, but not as much as a lab director? I want to hear the difference between research versus the production.
No, it's a very good question. I think it's in particular useful indeed to students and researchers also that are considering career options and so on to think through those kind of implications. So I agree. So as a professor, I'm trying to somehow, we're doing experiments, we're trying new methods to learn, like to understand better, like really how the problem, what's the hard part of the problem, what can be done, what cannot be done, and so on. As an engineer, as someone working on products and so on, you're really looking at it with a different lens, completely as you were saying. So I'd say there's certainly some of those papers, like in particular the ones on features that we're doing and so on. I think there's some of that stuff, not necessarily exactly the paper, but I would say there's certainly some of those ideas that I'm looking forward to figure out how to integrate in our products. Because we know there are shortcomings, and this is kind of an exploration of how we could kind of somehow fill some of those shortcomings. The 1D structure for motion work, for example, that's not something that I would think we need immediately to solve. Like if we build a device that needs to do some SLAM capabilities and so on, like even if it has a lot of radial distortion, we can calibrate that in advance very carefully. And maybe have a little bit of field calibration on top of it, but we don't need to cope with a completely unknown, radial distortion and these type of problems. So I think those are much more out of curiosity, out of, like I don't see a direct kind of need for it in the products today. But who knows? It's the kind of things when I did my PhD and we build this kind of, pipeline to go from images to 3D models. We thought it'd be cool and this and that. I'd never thought, that 20 years later, there would be all kinds of, products sold that have all these capabilities built in. Often it's also a time horizon thing, right? And of course, many things will never end up being used, but there's things that you don't expect today that they will be used and useful. And 10, 20 years from now, they might be like omnipresent and used. So it's somehow hard to guess, but yes, at Microsoft, I will not work on the things that I don't know how to, how to use in the near future, that I don't know how it fits already today. If I don't know today how it fits in the product, I'm not going to work on it, or, with limited efforts, or in a sense, in collaboration with academia to more figure out kind of what is the right direction, where we should be investing in this and that. But yeah, so I think that there's a very nice complementarity, and this is kind of what I like about my role. And I think, a lot of my colleagues also do, given, like many are on both sides of that fence in a sense, is really this kind of two sides looking at the same problem with in two very different ways. Yeah.
Thank you, Mark.
So I also have a relatively technical question for Mark. So there's one book you mentioned that the carefully handcrafted method, right, for feature matching outperforms both deep learning and the previous handcrafted ones. Do you think there's a room for combining this kind of handcrafted method with the deep learning ones? And in more general, right? So I think in this space, right? So what do you think there's a principle to combine deep learning method with those kind of geometric structures, or is really application dependent, method dependent, formulation dependent?
I think the principle at a high level is quite simple. In particular in geometry, there are a lot of things that we understand deeply at this point. Like in the 90s, and we really worked hard on understanding the whole multi-view geometry, the relation between images, how mathematically these relations can be described and so on. So we deeply and intricately understand those mathematical relations. These are things that have not super high dimensional, but highly nonlinear. And so it's 6-dimensional spaces, for example, functions that, will be a 6-dimensional function. I mean, like at the core intrinsically, but then it's somehow a blend of, or it's things that are blend functions that somehow combine, like in structural motion. If you look at it end to end, you actually have the structure and the motion, and you have the product of those two as a function. We've learned how to decompose that in small, very compact mathematical, pieces that explain, disentangle that essentially. Okay. If we would just do deep learning, we would somehow have to learn this space with a very intricate, complicated, highly curved somehow structure. We would more or less have to exhaustively cover it, meaning all the scenes from all the viewpoints somehow, and all the motions, like something like that, which essentially is not doable. so the key is so those functions would be crazy to learn them somehow. However, they are also in a carefully crafted structure of motion pipeline, for example. There are many steps where there's no first principles like mathematically derived kind of where we should put the threshold or where we should, what is the right measure to compare features or so, right? Like what is the right feature descriptor, those things. Those are places where there's a lot of room to actually learn it from data. Now, even there today, we often, learning has this, there's a problem with learning, which is that learning will in particular do well, will essentially overfit, right? Like it will essentially do like extremely well on all the benchmarks. And then you try it out in the real world, like on real world applications, where the handcrafted features have been, kind of tried out and crafted on like a broad set of things, and generalize very well because they build in some core principles and at high level and so on. And when you learn, you do extremely well on a particular data set, on a particular thing. But then if you go out and you try it out randomly, it often degrades significantly. And so that's, I think, where we really have to learn how to disentangle the problem in the part we know and we represent mathematically in a compact way with very few parameters that we can essentially compute. And then the part that we actually, that we know is not like modeled with a compact model, mathematical model, but it's something that, that's where we start putting heuristics in and this and that and so on. Okay, all that stuff, we have learned that at the meta level, we have learned that stuff we much better train from data. And there's still a challenge of having not a mismatch between the data we train it on and then the data we later want to apply it on. That remains that is much more of a challenge with learning methods. But there, I think there is a lot of potential. And that's the recipe, right? What we know and understand, we should really use. The key thing in doing that, right, is going from an end-to-end gigantic problem that you can never cover with data to a much more limited compact problem. For example, the TSDF fusion, right? There you have a very limited compact problem, which is like, okay, I have like some measurements and how do I integrate those measurements like in a very local, small space that you can learn. And that's doable to exhaustively cover and kind of have seen every possible example. And then you know it by heart. If I look at HoloLens, the hand tracking on HoloLens, that works very nicely because, a hand is not an infinite dimensional thing. It's a relatively compact thing. The possible pose of the hand is something you can, that you will see in front of when you wear a head-mounted display and you kind of move with your hands in front of it. It is a limited tractable space that you can exhaustively cover with data. And then deep learning is going to work fantastically.
Okay, yeah, agree. Yeah, thank you. Yeah.
We have a couple of more questions from the audience. One is, when you go from point clouds to line clouds for privacy-preserving localization, how does this affect the algorithmic complexity of the methods that you're using?
Yeah, so it depends, right? So let's say the P3P, if you move to lines in the simplest way, you move to 6 lines. 6 lines intersecting 6 lines, that's essentially a 64-degree polynomial. So that becomes actually quite painful and is also quite unstable and can, the ransack, the minimal solver will yield up to 64 solutions. So clearly that has a huge impact if you try to use that. As soon as you add the vertical, you go to a much lower dimensional problem, and then it's actually almost on par. And then there's some where even more. And then essentially there's barely a penalty hit. So it depends a little bit. So there are definitely, there are solvers that are, in normal circumstances where vertical and so on, or where you don't have a single isolated image to query from, but you actually have a sequence of images. Today, every device that we use, like AR Core, AR Kit, or HoloLens device, have a built-in SLAM system. So locally, they don't need to query the position for an individual image, but actually a sequence. So as soon as you have those additional constraints, the penalty for using line clouds instead of point clouds, is barely registers.
For the invariance learning, what factors do you think are important in feature extraction matching besides rotation and illumination?
so I mean, those are some of the big ones, right? I mean, in addition to that, you obviously have shearing and so on. So as you go to like going from rotation to more fine distortions, right? So obviously there's that. Being able to capture also go to like that's kind of the obvious next step is to also include the fine distortions. We've seen actually in the past that affine invariant features always in most benchmarks were losing out to SIFT. And that was exactly because of this problem, right, of discriminability. So often it didn't pay off to actually go to full affine models. But I think still, like in this type of model, you could actually put it in, and when it's actually relevant, you could leverage it. Beyond that, I'm not so sure. I mean, that would be the obvious kind of thing to add in. The scale is already captured anyways at the detector level. So yeah, not immediately, like I'm not immediately thinking of like another one that's like top of mind.
Maybe a final question from the audience, which is also something that I would be interested in. Has the research related to the Azure special anchors been published? And if yes, could you point to those references?
Well, indirectly in a sense, right? Like, so what we, there are, we're using methods that have been published. We are, our privacy preserving method, like gives you some ideas what we might be using, in the normal setting. In essence, we like, it's kind of, we're kind of doing the kind of usual things that you would expect to do. I don't know how much I want to really kind of spill the beans here, but I think if you do things properly, you kind of use the state of the art and so on. You can do a lot of things. But so we haven't explicitly published like our whole pipeline that we're using. No, we haven't done that, and we're probably not going to do that anytime soon.
Okay, thank you very much. Yasu or Michael, do you still have a question that you want to ask?
No, I'm done.
No,
That's
thanks.
great.
I'm great here. It's very inspiring talk.
Yeah, thank you very much for the great talk.
Thank you.
Thank
Yeah.
you. Bye-bye.
Okay, thank you.